Hi everyone, and welcome to Azure Storage for AI workloads. I'm Saurabh Sensharma, a product manager on the Azure Storage team focused on AI workloads. And today, I'm joined by my colleague Vishnu Charan from Azure Storage and Saloni Sonpal from Azure OpenAI. Today, we are going to walk you through how Azure Storage powers AI inference at scale, how we securely bring enterprise data to AI models, how we accelerate inference with high-performance storage, and how we reduce GPU idle time through faster model loading. Whether you're building on Microsoft Foundry, on AKS, or directly on Azure Infrastructure as a Service services, this session is built for you. This talk is focused on inference, the dominant AI workload today, and the unique capabilities Azure Storage brings to make agentic inference faster, cheaper, and more secure, including turning your enterprise data into agent-ready knowledge. This session is broken into chapters that map to each agenda item that you see here. So feel free to jump straight to the topic that matters the most to you. Before we dive in, let's quickly frame how Azure Storage and AI connect. We typically think about these two in two categories. First, storage for AI. Storage as a foundational element of every AI workload, from training and fine-tuning to agentic inference, which is the focus of today's talk. This is where speed, scale, and security have to come together. Second, AI for storage. Using AI to make storage itself smarter, from better data management and classification to day-to-day operations. Today, we'll focus on the first category, storage for AI. Before we go deep on storage for AI inference, let's set the stage on how Azure Storage plugs into the AI stack today, across training and inference, and how it gives you the freedom of choice to build applications on Microsoft Platform as a Service services, on Kubernetes, or directly on Infrastructure as a Service or IaaS, with open source and partner tools. At the infrastructure layer, the AI workload stack looks quite familiar. Physical infrastructure, GPUs, NICs, local NVMe, the same hardware story. Virtualization on top, VMs and Kubernetes nodes, again, the same playbook. But the differences emerge in storage, where AI workloads demand high throughput and low latency at massive distributed scales. Across three patterns, in fact: data prep, high throughput checkpointing during training, and model and data retrieval during inference. That starts with Azure Blob as the durable foundation, accessed through purpose-built storage clients, beginning with Blob Fuse for POSIX-like file access, ADLFS for FSPEC workflows, and the PyTorch connector for high-throughput data loading. For HPC class throughput, Azure Managed Lustre with the AMLFS POSIX client, and Azure Container Storage that presents local NVMe as persistent volumes for stateful Kubernetes workloads, with Azure Files, Disks, and Elastic SAN support on the roadmap. All of these are orchestrated across VMSS and AKS. We've optimized these clients to plug into the AI runtimes and orchestrators the developer community is using today. This includes Ray, PyTorch, TensorFlow, vLLM, SGLang, Triton, and ONNX. And this same foundation powers Microsoft Foundry, the AKS Kubernetes AI toolchain operator, or as we call it, Kaito, and the broader Azure AI infrastructure. Building on exactly this foundation, Azure gives you three intentional paths to run AI workloads, and storage is a critical element across all of them. Managed PaaS with Microsoft Foundry as the managed AI platform with access to Microsoft partner and open models. Great for teams who want abstraction. Managed Kubernetes with AKS for teams who want more control. Bring your own models and frameworks and orchestration, still deeply integrated with Azure Infra. Direct IaaS with VMs, storage, networking, and AI-optimized Silicon Direct. This is where hyperscale and mega-scale AI customers operate. Across all three, storage delivers the same outcomes, bringing enterprise data into the agent stack and powering fast, cost-effective, governable inference at scale. Let's look at agentic inference from a storage-centric view. Any agent that leverages enterprise data is built on a data pipeline anchored in object storage, or Azure Blob, with two stages. Stage 1. Bringing your enterprise data to AI services and agents. This is the data preparation pipeline. Ingestion, cleaning, chunking, embedding, and indexing into a vector database so that the agent can do grounded retrieval with the right context. Intermediate representations, namely the embeddings, indexes, process chunks, get stored on Azure Blob, so they can be retrieved with milliseconds latency at query time without rerunning the entire pipeline. Stage 2. Retrieve, store, and manage AI data at runtime. Every turn of the agent loop multiplies load on storage. More retrievals from Blob and the vector index, more test time compute, and an exponential explosion of logs, conversation state, tool outputs, and agent traces that all have to be persisted for fast retrieval downstream. At scale, distributed inference also swaps models in and out across GPUs. That gives us three critical storage requirements for agentic inference. 1. Making it easy to bring enterprise data securely to agents and converting it into agent-accessible knowledge. 2. Distributing and loading models onto AI compute fast enough to keep expensive GPUs busy. And 3. Optimizing infrastructure utilization to drive up tokens per watt per dollar. The rest of this talk maps directly to those three. Let's start with optimizing inference itself. And the biggest lever we have there right now is prompt caching. Now that we've set the context for top storage requirements for agentic inference, let's go one layer deep into where the next big wave of inference cost and performance pressure is showing up: prompt caching. As enterprises move from single-turn chat to long, multi-turn agentic workflows, the way prompt tokens flow through the GPU is becoming one of the largest drivers of inference cost and latency. My colleague Saloni Sonpal from Azure OpenAI and I are going to walk you through what's happening and what we are doing about it at Microsoft across Azure and Microsoft Foundry. To set the stage, let's look at how inference works today without caching. Modern AI agents run on long, static enterprise context, system instructions, tool definitions, retrieval context, and they invoke these prompt contexts across millions of invocations. In most production agents, the static unchanged portion of the prompt represents more than 60% of inference cost. Here is why. On every turn, the GPU has to recompute the model attention over the entire prefix, the static system prompt, the tool definitions, and all of those prior turns. Turn 2 adds even more history on top of that. And then turn 3 adds even more. By the time you're a few turns in, the GPU is burning expensive cycles, rereading the same tokens it has already seen before. That recompute is what drives up time to first token, or as we call it TTFT, and the end-to-end inference latency, and further, what makes long context agents so expensive to operate. Now let's apply prompt caching to the same picture. The idea is simple but very powerful. Instead of recomputing attention on every turn, we cache the KV state of the repeated context tokens and reuse it for the next turn. On turn 1, the GPU still processes the full prefix once, but as it does it, it also writes the attention state out as a context cached object. Turn 2, the GPU doesn't redo that work. It just loads the cache state and only computes the attention on the new tokens for that turn. Turn 3 and every turn after that looks exactly the same. The result is a dramatic reduction in GPU compute per turn, and customers can get inference cost savings up to 90% along with significantly lower time to first token. In fact, this is so impactful that model providers like OpenAI already offer implicit prompt caching APIs out of the box. That's a great starting point. But for enterprise scenarios our customers are building, implicit caching alone is not enough. And that's exactly what Saloni will talk about next.
Thanks, Saurabh, for grounding us in the core problem of prompt caching. At Microsoft Foundry, we think of prompt caching as an evolution. 3 distinct tiers, each designed to address different scale of workload. Let me walk you through them. First is implicit prompt caching, our fast by default option. The KV cache sits directly in the GPU memory alongside the inference engine, making it ideal for real-time agents, multi-turn conversations, and other short-lived workloads. It supports data sizes from kilobytes to low megabytes with TTLs typically between 5 to 10 minutes, up to about an hour. The key advantage is speed and simplicity. The model provider owns the cache and the API. The customers simply benefit from improved performance with 0 changes to their application. Implicit prompt caching is already supported in Foundry. The second tier is extended prompt caching. As workloads scale, whether longer conversations, richer media, or larger datasets, the limits of GPU memory become apparent. Extended prompt caching moves the cache onto the GPU node's local SSD, enabling hundreds of gigabytes of capacity and TTL of up to 24 hours. This is the cost-efficient scale tier, still managed by the model provider, but allowing customers to retain context significantly longer. Extended prompt caching is generally available in Foundry starting May 2026. Customers can set the prompt cache retention option to 24 hours or leverage it by default on GPT 5.5 or newer model deployments. Both implicit and extended prompt caching, however, are node-bound. If a request is routed to a different node, a different cluster, or even a different region, or if the TTL expires, the cache is lost, and the full pre-fill compute cost is incurred again. This becomes a limitation if it's a long-running agent, global workloads, and scenarios where context needs to be reused across the enterprise. That's where explicit prompt caching comes in. Foundry addresses this gap with Azure Context Cache, a first-class Azure resource purpose-built for storing pre-processed context in durable storage within the customer's own tenant. Built on Azure Blob Storage, Context Cache removes these size constraints, TTL extending to days or weeks or even months, and operates independently of the nodes, working seamlessly across sessions, deployments, and regions. The API is owned by the inference layer, making it portable across models and frameworks. This is the shift we are driving. Prompt caching as a core system capability of the AI platform, not tied to where your request lands, but delivering consistent, guaranteed savings wherever the reusable context exists.
Thanks, Saloni. Now let's go one level deeper into the Azure Context Cache. At its core, it's durable storage of model KV prompt objects inside the enterprise's own Azure tenant. The design of Azure Context Cache has 3 properties that make it enterprise-ready. First, a provider-only endpoint writes the encrypted KV state into the cache. The model's IP or intellectual property, the attention representation, is never exposed to the customer in clear text. Second, a customer or developer-only endpoint that gives the enterprise full control over time to live or TTL, retention, invalidation, and metrics. As an enterprise AI developer, you own the lifecycle of your own cache. Third, it's node agnostic and highly performant, delivering milliseconds latency and several tens of millions per minute of token throughput at global scale with a neutral API that integrates cleanly with Microsoft Foundry at the time of Microsoft Build 2026, and in future with AKS or Azure Kubernetes Services and third-party frameworks as well.
Thanks, Saurabh. Let me bring this home with the outcomes that matter most to our developers. First, cost and efficiency. Explicit prompt caching improves cache hit rates and delivers durable cost savings on the cache portion of your prompt. For GPT-5 class models, this enables inference workloads to scale economically. Second, throughput. We support multi-million tokens per minute throughput for GPT-5 class models, providing the headroom needed to run high-concurrency agent-driven workloads without any bottlenecks. Third, latency. Retrieving from context cache is orders of magnitude faster than recomputing the full prefill, translating directly into a step function reduction in TTFT or time to first token. In multi-turn scenarios, this also improves observed end-to-end latency as the system spends less time on the repeated prompt ingestion across the concurrent users. Fourth, security and control. This is a bring-your-own resource model with purpose-built protection for your model IP and secure access, all running in your own Azure tenant. This also preserves the enterprise-level access controls our customers are used to in Azure. And finally, observability. You get rich cache diagnostics and fine-grained TTL control, so you can tune the cache behavior per workload and clearly understand its impact. We're opening this up for gated preview at Build 2026. If you're building long context or multi-turn chats, long-running agents, or even globally distributed inference workloads on Microsoft Foundry, we'd love to partner with you. Use this link on the slide to share feedback and sign up for the preview. We're excited to see what you can build with Microsoft Foundry and Azure Context Cache together.
That is fantastic. Thank you, Saloni. Now let's go to Vishnu to learn how customers building agents with their own open source tool chains or their own models can leverage Azure Storage for prompt caching.
Thank you, Saurabh. Hi, I'm Vishnu Charan, a product manager in the Azure Storage team focused on AI workloads. Picking up on explicit caching, the reason that tier works is the cache no longer lives on the GPU node. It lives on durable Azure Storage. And once it's on Azure Storage, you get the full scale of Azure Blob behind your KV cache. Effectively, unlimited capacity, configurable retention, and multi-region reach. That same idea is also how we are meeting the open source community. 𝗦𝗽𝗀𝗀𝗀𝗀, is NVIDIA's inference transfer library, a unified API for moving model weights and KV blocks across memory tiers with a pluggable backend underneath. You can see those backends along the bottom of the diagram. We've contributed a first-class Azure Blob backend into that row. So any framework that already speaks 𝗦𝗽𝗀, like VLLM, Dynamo, TensorRT-LLM, or Ray, can now read and write KV blocks to Azure Blob with zero custom adapter code. The most immediate payoff is in LM Cache, the open-source KV cache layer widely used with VLLM. Through our plugin, LM Cache offloads KV blocks straight to Blob. So the picture is consistent across the stack. Managed customers land on Azure Context Cache. OSS developers land on Azure Blob via 𝗦𝗽𝗀 and LM Cache. Both paths put KV cache on durable Azure Storage that travels with the workload, not the node. And with that, let me show you what this looks like in practice. Here's what we've got running. An inference app on VLLM serving Llama 3.3 70 billion tensor parallel across all 4 GPUs on this VM, loading the model from a blob storage container. LM Cache sits alongside VLLM, building the KV cache. Now to drive it, I'm using a simple Python client that posts an OpenAI compatible request to that VLLM endpoint with a fairly punishing prompt, roughly 100,000 tokens of context. And there it is, 52 seconds for the first token. That's the GPUs doing prefill from scratch. The long context cold start everyone's familiar with. Now let's wire 𝗦𝗽𝗀 in. Here's the config. Chunk size 256, local CPU tier off, because I want 𝗦𝗽𝗀 doing the work, not a CPU cache layer. And here's the newbies. 𝗦𝗽𝗀 storage on, backend set to Azure Blob, async puts so writes never block inference, plus the storage account and container we're targeting. Now I restart VLLM with the LM Cache connector enabled and fire the same prompt. As tokens stream out, 𝗦𝗽𝗀 writes the KV chunk straight to Blob in the background. We pay GPU prefill once, but the cache is being populated. Quick look in the portal, and there they are, around 1,500 chunks, about 20 megabytes each, sitting durably in the container, the full KV state persisted. Now for the real test. I restart VLLM, wiping GPU and CPU memory for a genuine cold start. Same prompt. This time, 𝗦𝗽𝗀 streams those KV chunks directly from Blob into GPU memory. Watch the network. Here's end load. We are pretty close to the line rate on this 80 gig NIC. The bottleneck just moved from GPU compute to network bandwidth. Exactly the trade we want. And the time to first token, about 8 seconds. Just by streaming the KV out of Blob, the model loads roughly 6 times faster. That's the 𝗦𝗽𝗀 Blob plugin, turning a 100K token cold start from a 52-second wait into an 8-second stream. The 𝗦𝗽𝗀 demo you just saw was the inference optimization story. KV cache streamed out of Blob, so cold start don't pay prefill twice. But the KV cache is only half of the cold start story. Every cold start also has to load the model weights themselves from storage onto the GPU. For small models, that's seconds. For the really large ones, it's minutes. Now, I want to focus on that half. Fast model loading and distribution. Same problem, same fix. Saturate the NIC straight out of blobs. The 𝗦𝗽𝗲𝗍𝗀 model streamer is an open source loader for large model weights. It plugs straight into the engines people actually run in production, vLLM and SGLang. Drop it in, point it at a storage account, and it replaces the default loader. Cold starts are the tax every GPU pays when it comes up. Auto scaling out, recovering a failed node, rotating a model, or loading a fine-tune on demand. With the default loader, that tax is unpredictable and minutes long on the big models. So the bigger your fleet, the more capacity you're burning, just waiting for weights to land. Here's what Streamer does differently. It splits the model file into chunks, pulls them from object storage in parallel, stages them in CPU memory, and pushes those chunks to the GPU memory concurrently. The reads and copies overlap, so the NIC stays saturated and the GPU is fed as fast as the network allows. And here's the piece we built, the Azure Blob plugin for the 𝗦𝗽𝗲𝗍𝗀𝗧 streamer. Weights flow straight out of Blob through CPU into the GPU. The Blob container is the source of truth, and the NIC is the only bottleneck. And we get 3 to 6 times faster cold starts than the default loader consistently. Let me show it running. Same VM as before, ND96, H100. It has 8 H100s on board with an 80 gig NIC on the back. The model I'm loading is GPT-OSS120B, about 60 gigs of weight, pre-staged as safe tensor shards in Blob container. Same storage account, same plumbing as the Nixel demo, just a different artifact this time. Now I start vLLM. Standard vLLM serve command with one switch. Load format set to 𝗦𝗽𝗲𝗍𝗀𝗧𝗏 streamer. That's the entire integration. Point it at the Blob container and the streamer takes over. Chunked parallel reads from blobs, CPU staging, concurrent CPU to GPU copies, all overlapping. Now watch the NIC. About 86 gigabits a second on an 80 gig link, the NIC is fully saturated. The streamer is pulling everything Blob will give it, and the GPUs are eating it as fast as it lands. This is what loading and network speed looks like. And there it is, all 8 GPUs loaded, application startup complete, 60 gigs of weights into 8 H100s in roughly the time it took to say this. One more cut at model loading. This time at AKS scale. Everything I have shown so far has been a single pod, a single GPU box. But production isn't one pod, it's 100. And every one of them has to pull the model down before it can serve a single token. If you run the numbers, a 70B model is 140 gigs. 100 pods coming up together is 14 terabytes coming out of Blob all at once. You hit throttling, the NIC saturates, and cold start stretch 10 minutes. Every one of those minutes is GPU you're paying for and getting nothing back. So we built a distributed cache inside the AKS cluster itself. 0 changes to the workflow on top. Hugging Face loader, Blob Fuse, the 𝗦𝗽𝗲𝗍𝗀𝗧𝗏 streamer, they all sit on top of it unchanged. Underneath, every GPU node is both a cache and a client. Local NVMe RAID holds the hot data served at NVMe speed with 0 copy Sen5. Anything missing comes in over the network from a peer with ingress acceleration on the fan inside. First pod warms the cache, the next 99 read from inside the cluster, 2.5 times faster model loading on AKS. Let me show it. Here's the live comparison. 12 gigs of LLM weights loaded on a real cluster. Direct from Blob, 1500 megabytes a second, 8 seconds to load. With the distributed cache, 4000 megabytes a second, 3 seconds, 2.5 times faster. And when 100 pods come out together, they all read from the cache. Blob gets hit exactly once. That's Azure Container Storage's new distributed cache, built for AI on AKS. Distributed cache is in early access right now. NVMe class latency, throughput to local network saturation, Kubernetes native, and minimum to 0 changes on your side. If you're running AI on AKS, this is the one to try. Scan the QR, sign up for the early test, and we'll get you on it. That's the inference half of the story on compute. KV cache going out to Blob, weights coming back in, both at line rate. But none of that runs without data. The model itself, the cache, the context windows, the retrieved documents, all of it lives in storage. And for inference, the bottleneck isn't whether you have the data. It's how fast you can feed it into the GPU. So the question for this last section is simple. How do you get your data sitting in Blob in front of an inference engine as fast as possible? That's our third pillar. Bringing enterprise data to AI inference and converting it to agent-ready knowledge. So how do you actually get to that data from inside your AI stack? That's what this slide is about, and this revolves around one key idea. We meet developers where they are with native integrations across the entire AI ecosystem. If you look at that list there, BlobFuse and AZCopy on the data movement side, ADLFS, the PyTorch connector, the LangChain data loader on the framework side, plus the two ecosystem integrations you just saw demoed, Run AI Model Streamer and NVIDIA NXL. Effectively, whatever stack you're on, Python, Spark, Ray, PyTorch, or an agent framework, you get to Blob without friction. A few tools worth calling out here. BlobFuse gives you a POSIX-like mount, so you can treat object storage like a local file system. Same experience across VMs, containers, and AKs. ADLFS is the Python native FSPEC compatible interface, which makes Blob instantly usable from Dask, Pandas, and Ray. For deep learning, the PyTorch connector plugs directly into dataset, data loader, and checkpoint APIs. No custom code, zero config auth with Azure Identity. Then the performance critical parts for agentic and inference workloads. We saw Run AI Model Streamer cutting cold start times, loading models from Blob 6x faster. NXL drops us straight into NVIDIA's data movement stack with KV cache offload and high-performance model transfers across Dynamo, VLLM, Ray, and the rest. And the last one, the LangChain Azure Blob Loader. Faster ingestion and lower memory footprint when you're working with large document corpora. 5 to 9 times faster lazy load, 7 to 10 times faster lazy load against the community loader. So Blob isn't just scalable infrastructure underneath. It's deeply integrated into the AI developer ecosystem with high performance, secure, seamless access across training, inference, and agent workflows. And that's the OSS layer. Saurabh is going to take it from here and show how Microsoft Managed Infrastructure brings all of this together so customers get there without having to wire it up themselves.
Thank you, Vishnu. Fast model and enterprise data loading is exactly the kind of thing that takes GPU idle time off the table and improves the quality of agentic inference. Now, let's come back to the other half of the agentic inference picture, bringing your enterprise data into the agent as knowledge. In the past, we have shown how blob storage plugs directly into Microsoft AI services like Azure AI Search and Microsoft Foundry to turn enterprise data into agent-ready knowledge with just a few API calls. But many of you have unstructured enterprise data on Azure files as well, file shares, SMB workloads, lift and shift estates, and you need the same ease of getting that data into AI. For that, we've made Azure Files a data source for Azure AI Search with two ways in which you can bring this data over to agents. Number one, the Azure Files Logic Apps connector, a low-code path to connect a file share and create a vector or hybrid index. It, by the way, also handles reindexing as your data changes. Number two, the native Azure Files indexer in Azure AI Search for teams that want finer control over enrichment and indexing. Either way, the path from a file share to a RAG or retrieval augmented generation ready index is now only a few clicks or a few lines of code. And building on that, many of our customers are going a step further with Foundry IQ. Foundry IQ is Microsoft's unified knowledge layer for agents. Instead of every agent reinventing its own retrieval stack, Foundry IQ gives you a single governed knowledge layer that any agent in Microsoft Foundry can ground against. What makes this developer-friendly is that Azure Blob Storage is a first-class knowledge source for Foundry IQ. Just point Foundry IQ at a blob container, and your enterprise data becomes agent-accessible knowledge with security, lineage, and governance of Azure Storage already in place, and no glue code required. Foundry IQ also supports Azure AI Search indexes with Azure Blob or Azure Files data as well. And this is how we close the loop between your data plane in Azure Storage and your agent plane in Microsoft Foundry, going from raw enterprise data to grounded, governed agents in just a few steps. To bring it home, we wanted to give AI developers and storage admins a single place to discover the AI capabilities of Azure Storage and wire your data into agent inference fast. Meet Storage Center, a centralized hub for file, block, and object storage all in one place. You get a unified view of your storage landscape, usage, performance, redundancy tiers, and tools like Lifecycle Management and Storage Mover with rich visualizations that make it easy to stay on top of your Azure Storage estate. What we heard loud and clear from customers, partners, and developers is that this is the best place for both admins and developers to land their data, starting with Blob, and then connect it to AI. From Storage Center, you can launch into Storage for AI experiences we covered today. We are excited to announce a limited preview of this experience. Scan the QR code now on this slide to sign up. We'd love to have you in and try this out. So to bring it all together, we started this session with 3 storage requirements for agentic inference. Number 1, bringing enterprise data to agents as knowledge. Number 2, distributing and loading models fast enough to keep GPUs busy. And number 3, optimizing infrastructure utilization for better tokens per watt per dollar. Across the session, you saw how Azure Storage delivers on all of those 3. Azure Context Cache for explicit prompt caching in Microsoft Foundry, now in gated preview, as well the 𝗦𝗽𝗀𝗀𝗀𝗀 plugin that enables attaching blob storage to open source model runtimes for prompt caching. Number 2, fast model loading with AKS and IIS with container storage distributed cache in early access. And finally, Azure AI Search and Foundry IQ to turn your enterprise data into agent-ready knowledge. And to bring it all together, Storage Center as your unified entry point to leverage storage for AI applications. Here are some helpful references that you can refer to and supercharge your AI inference workload journey with Azure Storage. From Saurabh, Saloni, and Vishnu, thank you. And we can't wait to see what AI applications you will build with Azure Storage.